Okay, welcome to section 8.2. We're going to dive a little bit more into sequences and series. We already know what a sequence is. Well, now we're going to look at the series part of it, and we are going to be looking at series a lot. Okay, and all a series is you look at this infinite sequence, and you're going to add up all those terms. So it's a summation of an infinite sequence. So it's also called infinite series or a series. Now when we're talking about definition of convergence or divergence, you're looking at if that sum converges, then that series converges. If that sum diverges, then that series is going to diverge. So all of this is basically saying if the sum converges, yeah, so does your series. All right, so the first series we're going to learn is that telescoping series, or telescoping, potato. What this is it telescopes out, and you'll notice that we have those interior terms, minus, plus, those are going to cancel each other out. The b sub 3 is going to cancel with the b sub 3, the b sub 4 with the b sub 4, the b sub n with the b sub n. So what we're literally going to be left with is that first term and then that nth term. So this series is going to converge if this nth term converges. Because we already know what that first term is, because we will be able to generate that. That nth term, of course, we won't, because it's an infinite sequence, so we won't want to figure out what that is. So we'll take the limit of it. If the limit converges, then we know that series converges. Now we'll be doing examples of all of these series here in just a little bit, but we're going to learn all the series involved. Okay, the next series we have is the geometric series. Now this one has its own convergence and divergence test. So this one we will always use this test to see if it converges or diverges. And you'll want to use this test because it is super, super easy. Now when you look at geometric series, they are, to get to the next term, they have a common multiple, whereas the arithmetic sequence has a common difference. Okay, so this has a common multiple, and you'll want to find out what that is, and that's going to be your R. When you find the sum, if they want to know what the sum of that series is, you're going to take A, that first term, and divide it by 1 minus what that R turns out to be. Now the series convergence test, if that R is in between 0 and 1, and it's the absolute value of R, then you're going to converge. It's going to diverge if the absolute value of R is greater than or equal to 1. Okay, I told you that test was pretty easy. So let's take a look at these guys in action. So I'm looking at number 1 here. I've got 1 over n minus 1 over n plus 1. You've got that minus sign, so we've got a good shot at being a telescoping or telescoping series. Well, let's just find out what a couple of those terms are. So if I put 1 in there, I'm going to have 1 over 1 minus 1 over 2. And then I'm going to add that to the next one. So when n is 2, I'm going to have 1 over 2 minus 1 over 3. Plus, I'm going to have 1 over 3 minus 1 over 4. So it looks as though we are going to have that telescoping series. Now when I look at it, my first member in that series is going to be 1. The last guy is going to end up being that 1 over n plus 1 because this guy's going to cancel. Okay, so if I find out where this limit's going, and you can put the limit as n approaches infinity of 1 minus 1 over n plus 1, or you can write it as 1 minus the limit, like in the definition. It's going to get you the same place because there's no n here. That's going to stay a 1. So when I look at this, I've got 1 minus, well, as n gets really, really big, the denominator gets really, really big, the fraction gets really, really small. So this is going to have a limit of 1, which means that series converges. Well, that wasn't so bad. So this is one of those telescoping series. Now when I look at number 2 here, there's no n. So the first term's 1, the next one's 1, the next one's 1, and we're going to keep adding those up until they tell us to stop. So I could rewrite this as n, okay, 1 times n. So when I take that limit as n approaches infinity of my series, which is n, that's going to infinity, which means that diverges. It is not a series that we're going to be able to add up. Okay. All right, so let's look at this guy right here. I've got 2 over 4n squared minus 1. Okay, so when I look at that one, we're going to have to split this guy apart. Okay, so when I look at this, oh, that's a terrible little guy there, isn't it? Okay, I'm going to look at this as 2 over 2n plus 1, 2n minus 1. Okay, and I am going to do a little partial fractions. Oh my goodness. So I had a whole one fraction. I need to split that apart. So when I'm looking at this guy right here, I'm going to do my partial fractions just like I did with integration. So I'm going to rewrite this as a over my 2n minus 1 plus b over 2n plus 1. Okay. And then when I do my partial fractions, that's going to give me 1 over 2n minus 1, because a is going to turn out to be negative 1. Okay, so you're going to use your partial fractions just like we did in section 7.5. Okay, so now that I have it here, I can see, oh, I've got the minus sign, so I've got that same telescoping function going on. Okay, so when I look at that, if I put 1 in here for my n, I'm going to have 1 over 2 minus 1, which is 1. And then I'm going to have 1/3 plus. Then when I put 2 in there, I'm going to have 1/3 minus. When I put 2 in here, I get 1/5 plus 1/5 minus 1/7, and it keeps going. So those interior are going to cancel. So I end up with 1 minus that 1 over 2n plus 1. I'm going to take the limit as n approaches infinity of 1 minus, 1 over 2n plus 1. Well, this little guy is going to go to 0 again, so 1 minus 0 is 1, so it does converge. Okay. So just take a look at how different those telescoping examples were. The first one we did was set up ready to go. The second one, however, we had to use partial fractions to pull that one fraction into 2 separate fractions. And it all hinges upon, does your denominator factor? Okay. Now when I look at number 4 here, when I look at that, I could rewrite that as 7 times 1 over 2 to the nth power, which means now we're in geometric form. I want to look at the r. The r is what we're taking to a power. My r is less than 1, so that means my series converges. Now you can kind of see why geometric is going to be so much fun for us. Look at number 5. You've got something being taken to a power. That fits right into geometric. My r is equal to 3/2, which is bigger than 1. So that, my friend, is going to diverge. Goodness, with geometric series, we could do those all day. Okay, we've got some properties of infinite series. I'll let you read through that. Very similar to other things we've done, derivatives, integrals, etc. Now, convergence test. They are in the future just going to give us a whole bunch of problems, and they're going to ask us which of the following series converge or which of the following diverge. Okay, and like I said, some of those have their own specific test. Geometric series has its own test. You are always going to use that. Okay, other series don't have a specific test. Okay, so you've got many to choose from. The first test is the nth term test. When would be a good idea to use this test? It's good with fractions where the numerator's power is equal to the denominator's power, or the numerator's power is bigger than the denominator's power. Now, this is actually more or less a divergence test. If you take the limit of that nth term as n approaches infinity, if it doesn't equal 0, then it diverges. You have no problems. If the limit equals 0, this proves nothing. This shows nothing. It doesn't say it converges, doesn't necessarily say it diverges. What it does say is use another test. Okay, so be careful. If it doesn't equal 0, we can make a conclusion. If it does equal 0, we got nothing. Okay, so let's look at this right here. So when I look at my 2 to the nth power, I'm going to do my limit as n approaches infinity, and if any of these tests use limits, then you've got to make sure that you write that out as your first step, like that telescoping series. If that limit approaches or converges, then the whole thing converges. Same thing here. If you're using the nth term test, it involves a limit, you better show that limit. Okay? Now, when I look at infinity, n, or 2 to a very, very big power is going to be infinity. Okay, well guess what? Infinity isn't equal to 0. Therefore, this series diverges. Okay. So looking at this guy here, once again, I'm looking at that limit. Ooh, that was a whole bunch of m's on there. Oh, well, you get the idea. Okay, of n factorial over 2n factorial plus 1. Now, just remember, note, 2n factorial is not equal to 2n factorial. Okay, so be cognizant of where parentheses are. Well, when n gets really big, this 1 is not going to be significant. So we're really just looking at where this guy's going. Well, those n factorials are going to cancel, so this guy's going to go to 1/2. Well, 1/2 is not equal to 0. Therefore, this series diverges. Okay. Now, just to give you an example of one that throws us for a loop, if I had the series of 1 over n, I would look at the limit as n approaches infinity of 1 over n. Well, that would go to 0. Okay, this tells us nothing. Which means I would have to perform a different test to determine whether it is divergent or convergent. Literally, I can make no assumptions at this point. Okay? All right.